Hello, I hope I'm audible. Can anyone just check with me if I'm audible or not?
Yes, yes.
Okay, so let's start in 5 minutes. I guess people are still joining. Let's wait for them to join first. I guess most of us have joined, so let's start today's session. So uh, so a very good evening to all of you. I am Swastik Sharma. I am a PhD student at IIT Kanpur, and I have been given the responsibility of taking your doubt clearing sessions for the course that is Smart Grids, Basics to Advanced Technologies. This is being taken by IIT Roorkee by Professor NP Padhy and Professor Premlata. So, so I would like to give this disclaimer in the first class itself. So I've been doing this in the last course as well. So these are your doubt clearing sessions, right? These will act as a supplement to your regular lectures that occur in the NPTEL MOOC form. And in no way these are the substitute of those lectures. You have to first go through those lectures, then only you will be able to you will be able to appreciate what we are doing in this class. Otherwise, it, I have to cover 5 lectures that have been given you in a week. So covering 5 lectures in 2 hours and summarizing all of them, you would know most of the things, right? So what we are going to do is in the first hour or so, I'll give you a brief overview of what we learned in the first week. And then in the next hour, we'll solve some MCQs that will help you in solving the assignments. The assignments are fairly very easy. So consider this as a chance to clear all of your doubts that happened in the, that you may have when you went through the lectures in NPTEL. So so let's start. Just a second, let me share my screen. Yeah. So, we started with a brief introduction of the whole course. So, in the first two lectures, the instructor went over a brief introductory part about why smart grids are necessary for managing the uh, power system, especially in coming generation. So let's go over through most of those things. So here we have a conventional electrical grid. In a conventional electrical grid, what we have is we have a separate generation, which is meant for generating power. Then a transmission interface where the generated power is transferred from the generating side to the distribution side. And distribution side up until now was meant only for um consumption by passive consumers. That is, that distribution systems were not allowed to we can't say not allowed. I mean, they were not technologies developed enough or robust enough for the distribution systems to generate power. So mostly what happened due to the conventional nature, what we have is we have a top-down switching phenomena where the upstream or the top side is the transmission side, and transmission or the generating side where the bulk power is generated. And in the early 1900s, what happened was the Great War of Currents. You must have probably heard about it. It was the war between AC and DC, AC being led by Nikola Tesla and DC being led by Thomas Alva Edison. So what they were both arguing about is what should be the future of transmission. So should it be AC? Should it be DC? So ultimately, AC won because of the economical reasons at that time, because it was fairly very cheap to generate and transmit AC over the uh, long trans long what you say uh, network. So we can't say that it was economical. It was economical based on the technologies that were there in 1900s. So we know that DC would result in less losses. So now we are mostly the government is developing HVDC transmission sites. You must have seen the great transmission lines that are HVDC transmission lines that are there between Agra. When you went through on the Lucknow Expressway, anyone, if you have went on that Lucknow Expressway, you must have seen the HVDC transmission sites. So, so the main proposition of DC transmission versus AC transmission is that DC transmission, because the frequency is zero, it's a direct current, the chain effect and the proximity effect that is there due to the frequency inherent pulsating nature of the AC current, it's not seen anymore, and due to which power losses rest. Also, corona loss is minimal in DC transmission because corona losses occur because of the extra high voltages that ionize the air surrounding to that. This is less this is less prolonged in the DC transmission side because of no pulsating nature, just a single frequency of 800 volts. You will see less corona losses because corona losses is indeed frequency dependent. So, hence, they are very ideal for very long distance transmission, but they are not cheap yet. We still have to have, we save on losses, but the accompanying technologies, the converting stations and substations, etc., are still, what you say, expensive in nature. Mostly renewables located very far from load centers. These can be connected through DC lines for efficient operation. And DC doesn't require any synchronized grid connection. As you can see, AC needs to be synchronized with the grid, which is at a frequency 50 hertz in India or 60 hertz in US. Also, electromagnetic interference is reduced in DC. Can anyone tell me what is skin effect and what is proximity effect? If someone has any idea, or should I tell you? Okay, so how many people are there? We have 18 people. Okay, so what happens in skin effect? So, uh, s- yeah, someone was saying something. Yeah, go ahead. Okay, so usually in AC, what happens is AC being pulsating in nature, Due to their alternating nature, what happens is the time varying magnetic field is generated when they flow through a conductor. So due to this time varying magnetic field, eddy currents are generated. So AC is alternating in nature, and it develops magnetic field through the conductor it flows. And due to this magnetic field, what happens is it leads to the production of eddy currents. So these eddy currents, due to the inherent Lenz's law, they oppose the very the very mechanism that helped in formation of these eddy currents. So what happens is they oppose the magnetic field, or they oppose the main current that flows to the conductor. Due to the eddy current being the eddy currents are mainly found in the interior of the conductor, and the intensity of these eddy currents decreases exponentially towards the surface of the conductor. So eddy currents are mainly formed in this region, and their intensity decreases exponentially to the surface of the conductor. So what happens is, due to this effect, the eddy currents pushes the main currents to the surface of the conductor, and the main current that was supposed to flow in the conductor now is found mainly in the surface region, which we call is as skin depth. So in this skin depth only, you'll find the main AC current being flown. So this results in reduction of so we can see there is a reduction of effective area of cross section, or cross sectional area. So what happens? We know R is rho L by A. So if A decreases, the resistance increases. Now, when the resistance increases, what happens is the power losses will increase. Now, in proximity effect, so the similar thing happens, but in so the eddy currents are now produced inside the conductor, as well as the adjacent conductor, which is placed nearby to the main AC current carrying conductor. So what happens is, due to this, the eddy currents are formed in this, due to AC current being flown in this conductor, the eddy currents are formed in the opposite or the adjacent conductor. Now, these eddy currents push the main AC current in the other conductor away. So this is dependent on the direction of the flow of current. So let's say if the current in the both conductors are flowing in the same direction, the current will be found mostly in the uh, opposite side of the conductor. That is, let's say here and here. But if the currents are flowing in the opposite direction, the current density is more towards the surface of the conductors close to them. So this is what skin effect and proximity effect is. Both lead to decay in the resistance of the effective resistance of the conductor, which leads to increased power losses. Now in India, we have a National Load Dispatch Center, NLDC. Can anyone tell me what is it called? The NLDC in India? Recently, they changed the name as well. So if someone knows.
Grid India.
Yeah, so it's called, yeah, who told? Okay, so it's called Grid Controller of India Limited, or GCIL, or more compact form is Grid India. So it's GCIL. Earlier it was known as POSOCO. So each NLDC has divided itself into 5 regions. So these are North NLDC. So these are RLDC. So I will write NRLDC. And then we have East RLDC, West RLDC, South RLDC, and Northeastern RLDC. So what happens is, so these individual regions help in effectively managing the whole Indian grid. So what happened was earlier these were not governed by the common entity. These were separate in nature. In August 2020, in August 2006, what happened was apart from southern region, the northern and western and eastern region were combined together to a to a synchronized frequency. But in the southern region was connected in 31st, I guess, 31st December 2020, 2013, when we observe one India, one grid, one frequency, or we can write one grid, one frequency. So then only all of these five regions were coupled together to form a synchronized grid frequency. This was, I guess, initiated by I don't remember the exact link that happened, but yeah, I forgot the name of it. So these when they were linked, now we have a single frequency for the whole Indian grid, which is powered by the NLDC. So the main task of NLDC is to check. It's a load dispatch center, right? So its main function is to maintain the continual balance of generation and load. So if generation and load match each other exactly, the frequency will remain at 50 hertz. So can anyone tell me if generation is greater than load, what happens? Yeah, someone was saying. Yeah. So what happens when generation is greater than load or when generation is less than load? So I'm talking about frequency. Does it dip? Does it rise? Does it fall? So frequency rises when generation is more and decreases when generation is less than load, right? Now there is so this is how the NLDC ensures that it ensures continual balance of generation and load so that the frequency remains between a particular bandwidth. Can anyone tell me what is the uh, bandwidth in which uh, for normal operation of the grid, what is the frequency bandwidth? So in the recent Indian electricity grid code, it's mentioned. Does anyone know the frequency range or optimal range for normal operation of the grid? Anyone? Okay. So it's 49.95 to 50.1. So this is the frequency range for normal operation of the grid that has been mandated in the Indian electricity grid code, which was recently issued. So so apart from this, we also have major HVDC links with other countries. So we import and export power to Bangladesh. We export power to Nepal and Bhutan as well. Similarly, we are imploring the possibility of an Indian Sri Lankan HVDC connection. So this would be 285 kilometers in length, and this would serve as a purpose of for an HVDC connection between Madurai and Anuradhapuram in central Sri Lanka through the Park Strait. The Park Strait is the Ram Setu or the Adams Bridge that we call. So in first slide, you must have seen that the data was a bit old. It was 2016 to 2017 data. So for your reference, I have added the installed generation capacity as on 31st May 2023. So as you can see, still we have 56.8% of power being generated from fossil fuels. So if someone has question, they can straight away ask. Otherwise, I would ask them to please mute themselves. Um, if someone has questions, they can please unmute and ask. But I would ask you to please mute yourself so that I can also concentrate. Yeah. So a total of 56.8% of our electricity still comes from fossil fuel, and the rest of it, the 43% is the non-fossil fuel one. So this includes renewables with hydropower. So we have a total of 411 gigawatt approximately as on 31st May 2023. And currently, our nation has a target of achieving 500 gigawatt, I guess, by 2030, coming from renewables. So this doesn't include hydros. should tell you. So why am I saying renewables including hydro? I mean, hydro is also renewable, right? Doesn't even know why we don't quantify on what is the basis of not quantify hydro into renewable. Can anyone tell? I mean, most of the other nations worldwide you do that, but why India? Hmm? Okay. So so renewables are generally connoted as greener and cleaner forms of energy production. But the large hydropower plants, I mean, in the range of greater than 25 megawatt, what happens is we change the course of river. So mostly I'm saying we change the course of river. Those are also called run-off river project. I should mention. So this results in displacement of a large number of fish bodies or fisheries, and moreover displacement of the accompanied inhabited places. So usually for power plants greater than 25 megawatt, we don't connote them as cleaner and greener forms of energy production. But yeah, for small hydropower plants that are less than equal to 25 megawatt, we include them in our renewable energy sources definition. So this is also policy dependent. Let's say if India wants to showcase that they have achieved this much renewable power. So in COP26, I don't remember if it was COP26 or earlier one, we generally included hydro in renewables as well. So in Indian jurisdiction, we don't do that, but in international jurisdiction, just to show that we have achieved certain renewable power generation, we show that it's a hydro. We include hydro in it, so you can see hydro and small hydro are both added separately into that. So I just wanted to give you a quick comparison of how India is doing in comparison to its developing nation counterpart, China or other developed nations. So as you can see, United States and France and United Kingdom are developed. So they have reached a stagnant growth of electricity generation, which is at 4,000 terawatt hour. So this electricity generation is basically for the whole year. That is, we are producing this much amount of electricity, and it's being consumed by the mass population. But as you can see, China, which has the second highest population in India, which has the highest population, China is continuously growing its electricity generation needs, whereas India, it's still growing, but it's not growing as much as its Chinese counterpart. So that's where we are lacking. So this is one place that the government should focus, and it's focusing right now, and it's increasing its generating capacity year on year. Now, so so this was the whole idea of electricity generation and the stuff of how Indian grid behaves. Now, as you can see, we are increasing at a very high rate. Let's say Indian capacity, I mean, it's increasing still. So this increase necessitates that we start exploring the smarter grid options. So hence we need a smart grid that is able to power the electric grid of future. So why is the smart grid needed? So we have a wide geographical spread, that is, our load centers and the conventional sources of energies are located very far away from each other, and hence we need them to communicate and exchange information and operate and have interoperability. So for that we need smart grid. Also, there are a large number of interconnections. This can be due to political influences, economics, environmental reliability, and stability issues. Also, we have a rapid growth in demand. This is due to the fact that there is an increase in population. Also, the lower class has evolved into middle class, and since these classes have evolved, the electricity production generation electricity consumption also increases with it. Also, power system components are operated closer to their design limits. That's what happened during the Great Indian Blackout of 31st July 2012, and high penetration of renewable energy sources. So what happens is that let's say we have solar. So solar is mostly during the daylight hours, right? So due to which what happens, let's say with time. let's say our load varies something like this with the early morning peak and the evening peak, right? So I should provide like this. Okay. Now solar is generally, let's say this is 6 p.m. and 6 a.m. and this is 16. Let's say solar operate mostly between 10 and 2. So between 10 and 2, what happens? To draw in. We have a huge, I mean, this is a very huge, I am not drawing it to scale, so I'm just showing. So we have a huge influx of electricity due to solar power generation. So what happens? The loads are generally, sorry. So we see a huge decrease in net load. So this decrease in net load necessitates that accordingly, we observe a ramp rate. What is ramp rates? The ramp rates are the total increase. So ramp rate for a conventional power generation, a ramp rate is to increase in, or I should say, delta kWh, that is increase in generation or change in generation per unit time. This is the ramp rate of the system. So here you can see the ramp rate is huge, this and this. So to be proper, yeah. So to serve the load, what we need to do is we need to make sure our faster ramping sources are able to so provide services to this load. So we need better cooperation and better coordination. So for that, smart grids present a better opportunity and also competitive electricity. So what is happening right now is we are seeing retail markets in place. Right now in India, you see that consumers don't have much options. Whatever distribution utility buys, they pay you. But with more and more privatization, what is happening? You see that we have now, let's say, Ambani's distribution company, then there is Adani's distribution company, or Tata Power Discom, or another Discom. Let's say we have multitudes of Discom, and each we select based on right now the prices are controlled, but let's say both of them provide different rates for electricity. So what you want to do is you want to define what discom you want to choose, and from that discom you want to have the power delivered to your home. So for that we need a real-time monitoring, and it's only possible with smarter grids. So what is smart grid? A smart grid a smart grid is something like this figure shown over here. So we have different domains. So we have a transmission domain, a distribution domain, customer domain, generation domain with the electrical flows and information flows between each of them and between markets, operations, and service provider. We'll explore these in the next slides. So what exactly is a smart grid? A smart grid has the smart infrastructure, it has smart communication, it has smart management and smart protection. So what is smart infrastructure? We generally have two different ways in which we define our smart infrastructure. One is smarter energy system with smart power generation, transmission and distribution, and smart information system with smart meters, sensors, CMUs, and information management. So, so what is the major difference between all of between conventional generation, smart power generation that I just told, and there is one more distributed generation that I'll tell you. So in conventional generation, it was just assumed that the whole transmission grid provides electricity to the distribution side, and there is no reverse power flow between distribution and transmission. But now, in smart power generation, due to the enabling of two-way communication between customers of the smart grid and other participants in the smart grid environment, we have uh, resources distributed generation in at places at different distribution levels as well. So for them to be able to transmit power to the transmission network, we need a smarter power generation. So for this, we need advancements necessarily. These must be in transmission side and distribution side. For transmission side, we need smart control centers, we need smart power transmission networks and smart substations. And for distribution side, because of distributed generation, there should be a power flow direction interchanging. So earlier, as I told you, we generally had in conventional power grid that the distribution side is passive. Passive in the sense that they only consume load. They only consume electricity. But now distribution side is becoming more and more active. So the consumer has shifted from being just a consumer to a prosumer. So what is a prosumer? A prosumer is someone who produces as well as consumes uh, anything of utility. Here, let's say it's electricity, right? So the consumers are now becoming more and more active, and with that, their role has evolved into being that of prosumers. So for that, we need them to be able to supply power to the grid. There needs to be a reverse power flow. Also, microgrids. So what are microgrids? Can anyone tell me? I mean, it can be wrong. I don't really. Okay, so microgrids are generally uh, so these are what you say institutions. I mean, institution is the wrong word, but that's what came into my mind. So these are institutions where we have generation as well as, yeah, small generations, but with loads. So we also have loads in them. So these are able to supply power to the loads as well as direct power to the main grid. And in case when the main grid fails, they are able to self-sustain or self-heal by supplying power from the distribution generation available in the microgrid to the loads that are connected to the microgrid. So generally what happens is we have a main substation, transmission substation. So there is a PCC. We may have load connected here, someone installing a PV, let's say. Another bus where we have different DERs, let's say wind. So, and so what happens is, so when the main grid is, let's say, not able to direct power or there is something, so some breaking happened, let's say. So the microgrid are able to self-sustain in the sense that they are able to provide fend for themselves when the main grid is not there, and they are also able to feed power to the main grid when needed. So, so what is smart information system? A smart information system includes smart meters as well as smart monitoring. So what is smart meter? So smart meter right now, let's say earlier what used to happen, you had this these analog instruments in your home, right? Where some person will come analog or digital. Earlier they were changed to digital. So some person, a meter reader is what we used to call him, will come and read the reading of the meter monthly, and after that your bill will be processed. But now the systems have changed due to the development of communication infrastructure such as 4G, 5G. Smart meters are installed at various different places and even at your home. So what happens? These smart meters are able to communicate the data related to your consumption and other necessary things like voltage in the current that it's feeding into your power station, the power factor, etc. This is directly visible to the utility. So what the utility? So we have a lot of data now. In the age of AI, we when we have a lot of data, what we can do is we can manipulate that data. We can manipulate the data to be able to tell what kind of load was connected to your system. This is called as non-intrusive load modeling monitoring. So let's say you had a fridge at your home, right? You know its rating, but well, let's say you don't know its rating. You have no other option to know its rating. You are just suspecting that bill is being increased due to this load. Now, how will you do it? You will manually turn on circuit breakers and break all other connections of loads to your to the transformer that is connected at your home, and you will check if what kind of load it's consuming in 24 hours. So is this a normal way? I mean, no, right? You won't be wanting to shut down all of your electricity just to check how much load is being consumed by a particular appliance. So for that, you do non-intrusive load monitoring. So what is non-intrusive load monitoring? With the smart meter data, you have event detection. Let's say, um, so I hope my diagrams are like good, but I don't really have any other options. So this is T, and let's say this is the energy or kWh, right? So let's say you had the appliance off, then you turned on, you off, and you turned it on for a small duration, let's say. So what happens with your energy consumption? It will create spikes. So it will be like this, then it's like this. So these spikes will act as events. So these are events. You are turning on something, there is an event. So it would be checked at the place that your device is connected or the smart meter is connected. It will be able to tell this change in energy consumption, and from this change, you could tell what kind of load is connected to your so what load has consumed what amount of electricity. So this is one, but yeah, this can be done at the utility scale as well. They also have all of your information. So this raises concerns for privacy because they can monitor the kind of load that you're using. So let's say you leave home for 7 days, you won't use certain appliances. They'll know that these appliances are not being used. So this hurts your privacy, right? So NILM or non-intrusive load monitoring is done at a scale which doesn't hurt the privacy of the customer. So also, for smart monitoring, what we require is PMUs. As I told, so there are a lot of different devices connected across the power grid. So to tell where a particular fault took place or where something happened, you need to measure quantities relating to that. But that can be voltage or current. Let's say you want to measure let's say you want the phases related to voltage and current from that place or something, some place. So what you do is you install phasor measurement units. So what are these units? These are also called eyes and ears of electric grid. So the whole system is being monitored using only the PMUs that are connected at different places, so identified places. So you are monitoring continuously the phases associated to those measurements. So I digress. So I should first tell you. So can anyone tell me what is a phasor? So what is a phasor? Does anyone know? Okay. So can anyone tell me what is a vector? So let's make this class a bit lively. I mean, let's have a two-way communication here as well. I mean, it's like it's a conventional power grid. I'm just the transmission side. I'm just feeding power to you. I mean, you should be able to tell. Yeah, someone just wrote phase angle between voltage and current. I mean, it's phase angle, but I am asking what is a phasor? It's a quantity, right? What is a phasor? So phasors are rotating vectors. So you must have heard, right? Scalars and vectors. Scalars are just magnitudes of quantities, while vector has both magnitude as well as direction. But in case of phasor, phasors are rotating vectors. So let's say we have two bus systems, and bus one and bus two are connected, and we use a common reference signal. So this common reference signal, so in respect to a phasor measurement unit, is a cosine signal which is synchronized with universal time clock or GPS, right? So why we do this is because we want all of the measurements to be synchronized. We don't need to see that, let's say, a phasor measurement unit installed at remote location A and phasor measurement unit installed at remote location B both have different uh, uh, sampling different sampling synchronizing differently synchronized. Let's say it's giving me data every 5 minutes while it's giving me data every 2 minutes, every 10 minutes. So we need them to be synchronized to just one time signal. So we can't say it's synchronized to UTC while that is synchronized to ISC. So for that, what we do is we use a common reference signal, which is a cosine signal, which is synchronized to GPS. So this cosine signal, when we use our signal connected at bus 1, let's say we are measuring the voltage. So we measure the difference between the phase angle. So between the cosine signal as well as the voltage signal at bus 1 and bus 2. As you can see, we have delta 1 difference with voltage 1 leading. Sorry, it's like we can't say leading and lagging, but yeah, it's leading with respect to the bus 2 voltage. So we have V1 here and V2 here. So the length of the this arrow denotes the magnitude of the quantity. So so this is the phasor representation. So we know that it's rotating anti-clockwise and it's making delta 1 angle with respect to uh, the common reference signal. So what are basically phasor measurement units? The phasor measurement units are used to measure these phasor representation of quantities only, be it voltage or current. So how do they do that? So they have four different. So so they have four main functions. One is signal acquisition. So at first we would want the signals to be taken from the remote places, right? How will we do that? We can do that by combining PMUs with a voltage transformer or a voltage sensor or a current sensor connected to the substations. So from there, we can acquire signals pertaining to the voltage and current at that particular substation. This is then, yeah. And then we want time synchronization. Obviously, we want all our signals to be synchronized. Otherwise, there's no point if we have different synchronization. Third, we want to be able to process those signals. So I'll come to this point later when I explain everything in detail. And fourth is the data transmission aspect. So, so these analog inputs that you can see here, these are used to these analog inputs are basically the quantities that are being measured by the or the waveforms that are being measured by um, the PMU. These are passed through an anti-aliasing filters. So what are these anti-aliasing filters? What we have is, let's say we have a quantity. So we are measuring that quantity at a particular time interval, right? So this is how we are measuring these quantities. So let's say these are some n numbers of cycles per n number of samples per cycle, right? But what if I just measure these? With green, let's say I'm just measuring at only the peak time and every one sample per cycle. So what will we get is the signal will be something like this, right? So this signal does not correspond to that of uh, the uh, the the signal that we want to interpret by the phasor measurement unit. So what we do is we sample it multiple times. So for that, anti-aliasing filters are used, and these are then converted to digital signals, which is then uh, synchronized with the cosine signal from GPS, and time synchronized with GPS, which are then passed on to the phasor microprocessor, where these quantities are changed into the phasor quantities. And with modems, we transmit these quantities to different control centers. So that is how phasor measurement units work. This will discuss in detail when we come to I guess third week or fourth week, where we discuss the different elements of the system. I just wanted to give you a brief overview. Okay, so also for that we need communication. So there are two main types of communication. One is wired. We have power line communication and fiber optics. So both are wired. We require a physical connection to different places where you want the communication signal to be interfaced. This can also be wirelessly delivered, which can be through cellular or radio mesh topology. And these are being governed through some smart grid standards. So, what, why we require standards is, so what we are doing is we are repeatedly employing a technical task. So, how can we make sure that we don't make a mistake when we repeatedly employ that technical task? It's by adhering to certain rules and conventions. So these standards give us those rules and conventions to be able to replicate those tasks. So here we have IEEE 1547. This pertains to interconnection of DRs with the grid. And there is also IEEE 2030, which are interoperability standards. We'll discuss more when we come to the standards part. So I discussed in the first three, I guess. Yeah, here, different smart grid domains, right? So let's look at all of these domains a bit closely. So first, we have a customer domain. So what exactly is a customer domain? A customer domain is the area which reflects the customer of electricity, right? So these are so we differentiate our customers based on the amount of quantity they consume. I guess this is not visible, right? So if it's less than 20 kilowatt, these are residential customer. 20 to 200, it's commercial, and greater than 200, what we have is industrial loads. So this is how we bifurcate our customers into different quantities based on the power consuming capacity. So these are further, so the boundary is controlled by the energy service infrastructure. This energy service infrastructure houses the advanced metering information, infrastructure, which which encompasses your smart meter readers and smart meters, these IEDs, RTUs, and different metering infrastructure. So these are used for the at the customer periphery to be able to convey or make a two-way communication link between different entities at the smart grid domain and the customer domain, each being serviced by the energy service infrastructure. Then we have markets. So the markets are generally pool-based. So what is pool-based is that different customers or consumers or buyers and sellers come into a place. They put in their bids and offers, and based on those bids and offers, uniform trading or marketing, uniform market prices develop. So this markets is especially uh, developed for aggregators. So these aggregators basically aggregate various distributed energy resources. Aggregation of DERs at the distribution domain. What happens is these come into these markets to purchase or sell electricity. So then we have service providers. This is the another domain where all the business or the filing of accounts, billing management, etc., is taken care of. Then we have operations domain. This is the backbone of smart grids domain because the other smart grid domains, because this handles the um, what you say careful operating of the whole system. So without this, the security may security of the whole system may violate, which will lead to cascading what you say failure of the whole smart grid. Then we have generating domain where we have transmission and different generating resources which are connected with the market. And also, I have mentioned pump storage specifically. This is because I wanted to tell you if someone doesn't know what is a pump storage. So let's say that uh, uh, there's a scenario. Let's say the grid suddenly faces decay in load. What it assumed would be higher is suddenly very low, and the generation is greater than the load consumption. So what will happen is this would lead to uh, a fast rise in the frequency. So for this to not happen, what we do is the government usually we would turn off different generators if we want to, but it's not that easy. It's accompanied with different other aspects of the generation. But what we can do is we can install pump storage. So what does this pump storage do? They have two different reservoirs. Let's say there is one reservoir at a very low height, another reservoir at a very high height. So at generation greater than load, what they do is they consume that generation to transfer water from the lower reservoir to the higher reservoir. They act as pumps. Now let's say another condition happens when load is greater than generation. So frequency will dip. For that, generation needs to be generation needs to be increased. So what they do is they transfer this water from higher reservoir to the lower reservoirs through turbine, which leads to generation of electricity. Hence, these pumped storage act as what you say is uh, frequency regulators for the grid. So these are very good frequency regulators. Okay, so other we have transmission domain, which encompasses various ISOs, LDCs, the measurements on different quantities. Then we have distribution with distributed generations, transmission with customers, and other dynamics. So I know that you have went through Premlata ma'am's where she covers all of these domains in depth. So so why do we require standards? So I told you standards are what? These are rules these are rules and conventions for you to repeat a technical task so that each task is repeated uh, as it's supposed to be. So it's exactly reproducible. So for this, standards have some rules and guidelines. These rules and guidelines are there for safer operation of the whole circuitry and to make it economic. So for these standards are usually developed. So we have various different standards. We'll discuss it afterwards. So this is required so as to be able to have same task reproduced many innumerable times. So we have different organizations that develop these standards. We have NIST, National Institute of Standards and Technology, NC, IEC, IEEE, ISO, and ITU. And these organizations help in development of these standards, mainly IEEE, which we follow. So let's talk about some standards. So we have IEEE 1547. This standard particularly deals with interconnection of DRs into the power grid. So what we have is that so so these let's say we have main grid, we have the load, and we are having some PV, have some wind turbines here. And yeah, so this whole microgrid environment is connected to the main grid at this point, right? This point is called PCC, or the point of common coupling. So at the point of common coupling, what we want is that the microgrids must not regulate the voltage at these PCC. So what will happen is the main grid, which is responsible for which has higher bulk generation, or which has a higher what you say operating cost. If the microgrid start manipulating the voltage at PCC, the equipments could get damaged at the transmission side. So so to make sure that it doesn't happen, we the standards layout procedure for the that microgrids should not actively regulate the voltage at PCC. So this is generally done by producing standards related to the proper interconnection of these DERs to the um, power grid. Also, they lay down foundation for grounding approach, for which the microgrid should not create over voltages, so that the power rating of the equipments are not exceeded. And also, they lay down procedure for our ground fault protection coordination and etc. So you must have went through these lectures where she discussed about these standards in detail. Also, there is time synchronization. This is generally done with GPS, with respect to GPS and other such. I should have discussed this later on. Okay. So GPS and other standards, and then we have wide area situation awareness. So wide area situation awareness is generally for monitoring and preventing blackouts, and these generally house the usage of PMUs and etc. Then also there is substation automation and cybersecurity. So let's go in detail. I discussed these. So LAPS is nothing but local area power and energy system. It's another name for microgrid, you can say. Then we have IRID-B, which is time synchronization standard, which has the accuracy of, which mandates the accuracy of 1 microsecond. Then for wide area situation awareness, it generally used for monitoring and preventing blackouts. So in IEEE C37.118, lay down the proper rules and regulations for PMUs. So PMUs, so these are measuring a quantity, right? They cannot always be accurate, but to make sure that their accuracy is within a tolerable range, let's say 1% in steady state, these standards lay down these rules. So this rule says that the total vector error, TVE, must not be greater than 1% in steady state. And there is then IEC 62351 for cybersecurity and IEC 61850 for substation automation. This is basically a communication protocol for DERs and intelligent devices. So we'll discuss about this further. So these house for proper insights for the grid, what we mandate is the use of advanced metering infrastructure. So what is advanced metering infrastructure? Let's say your house is connected with some smart grids, right? And these smart grids are capturing data pertaining to the voltage, current, phase angle, power factor, your power consumption, reactive power consumption, and sorry, it's this it and the energy consumption, right? So these smart meters then so there are two main different so there is two different ideologies. These smart meters can either directly convey data to the MDMS, or they can use a vendor-based proprietary. So the direct communication is usually not preferred because of the increased costs related to their installation. So what we have is we basically use the other way around. So these smart meters are interfaced with neighborhood area network using power line communications or radio frequency of 900 megahertz, where it is then connected to meter concentrator, which concentrates all of these data from different smart meters. And this smart meter is then sent to the MDMS, which is the meter data management system, which houses the head-end system, which over this head-end system overlooks the entire operation of communication of smart meters with MDMS. Next, we have distribution automation. Now, so distribution automation generally comprise of SCADA, which is supervisory control and data acquisition, and IEDs and RTUs. I mean, with the advance of IEDs, RTUs are not used anymore, but let's say, and we also have PMUs. For distribution, so the PMUs are generally very expensive and bulky. For distribution systems, we have newer PMU, which are called micro PMUs. These micro PMUs are compact and not very bulky, and fairly inexpensive. So this can be these are used at the distribution side for better distribution automation. So what happens is, let's say, in what exactly is distribution automation? So we have a whole distribution system, let's say, and which is connected with the distribution substation. So this distribution substation, what it does is it converts 11 kV to 440 volt. So it has a circuit breaker, a switch, which is connected to a capacitor bank, then a recloser, then some more switches, distribution transformer, another recloser, another transformer, then a switch, and another transformer, which is the primary side. So you have different technologies connected to these to different nodes. With each node, we also have IDs connected to them. So these IDs convey data pertaining to voltage, current, and other stuff to the communication network, which is then processed at the data and control center. So this whole thing helps in proper management of the distribution system. So you want to automate everything. You don't want to go to a certain place just to isolate a fault. That's not what you say a smart choice, because since you have these intelligent devices, why won't you use them to be able to control the network in a way that suits you? So for this, you have different IEDs which convey these data to the distribution or control center, where a person sends commands remotely to the different sections. So as you can see, there is a recloser. Can anyone tell me what is a recloser? How is it different to switch? Anyone who has gone through the lecture would be able to tell me. No? Okay, so a recloser, what it does is it continuously senses the current, or what you say, the current through it. And as soon as it senses a fault, what it does it tends to isolate it, it breaks it. It's a kind of a circuit breaker. But then after a certain amount of time for which it is trained to, it then reconnects the grid, reconnects the network to the grid. So as to see if the fault is either temporary or permanent. A fault can be temporary, right? So if it sees that the fault is not decaying after reconnection as well, so then what it does is the sectionalizers which are connected to it then open the circuit. Sectionalizers are switches only, and hence that's the work of recloser. It senses and it then tries and attempts to reconnect to the grid. So this is how the whole distribution automation work. Different uh, instruments help in proper monitoring of the whole distribution system, and the whole distribution in these whole instruments are connected with IEDs which send data to the data center, and through these IEDs the person sitting at the center could issue commands remotely. So I wanted to discuss more on AMI. So mm, I guess that's it. So does anyone have doubts? If you have doubts, I'll take them and then we'll move on to question answer to some sample problems. Anyone who has doubts?
Sir, it's almost clear.
Mm-hmm. Hello. So someone was saying something, so I couldn't hear them properly. If they could just. So can you please say again? So I was not able to hear you properly. No.
Yes, sir.
Yeah, yeah. So tell. What were you saying? if you're not able to, if your connection is slow, can you just write in the chat so that I can see them? So it was Nitya. If you can just write in the chat section, so I'm not able to hear you properly. I mean, your voice is breaking.
I said it is clear. If any doubt, I'll just text.
Okay. Okay, sure. So, so that's it from this week. So let's move on to the questions. So let's discuss these questions. So I have two kinds of questions. One is a multiple choice question, and the other are multiple select. So NPTEL, they can ask you both. So keep that in mind when you are answering questions for assignments. They are two different kinds of questions. Either it's MCQ or multiple select. So, so the first question: who is the father of AC distribution system? Does anyone know? This should
Thomas
be
Edison.
Thomas Edison is he's the father of DC distribution. He would be very angry with you right now. Yeah. So it's Nikola Tesla who was the father
Okay,
of
sorry,
AC.
sorry, AC. Okay, sir, sorry, AC.
Yeah. No worries, no worries. Yeah. So I didn't go through the distributed generators, but the that Padhy sir covered in second lecture, I guess, in this week. So there he told you about disadvantage of geothermal waste technology. So can anyone tell me what is it? So you can go to the lecture slides as well if you want to. Can anyone tell me? So I didn't go through them because it was a huge, um, it was a very big lecture. So to cover this in 2 hours is very difficult. So can anyone tell me what is the disadvantage of geothermal based energy? Yeah, it's environmental impact. Then we have what is the function of smart information system? So is it generation? Is it integration? Is it analysis or all of the above? So an information substation should be able to integrate as well as analyze different information that it receives, as well as generate information pertaining to different sciences. Yes, it's all of the above. Then we have in the service provider domain, which of the following is part of account management? Can anyone tell me? So what do you mean by managing account? It's generally, is it customer relationships? I don't think so. And it's not about monitoring and controlling the building energy. It can be managing the customer supplies business account, not the billing information. No, it's the customer account. It's the account management, not billing management. Okay, so in the smart grid, the distribution domain will communicate more closely with the operations domain in real time to manage what? So we know that distribution system or distribution domain will have generations now, or we can say distributed generation. So to be able to So to be able to maintain the overall what you say, normal operations of the whole network, it must be able to tell, it needs to tell what to the operation side. No, so the consumer billing will be told to the service provider side. So I told you, so let me go back to this slide. So the server provider is the someone who manages the business as well as billing management, right? So, so when we have reverse power flows or we have power being fed from the distribution side to the transmission side, what we need to convey to the operations domain for successful operation of the system is the power flows. So you can go to the slide, third lecture slide. There you will find this. So which of the following standard represents the interconnection of distributed energy resource? Can anyone tell me? We just recently covered this.
IEEE 1547, C option.
Yeah. Then the meter concentrator is responsible for supporting communication with the meters over what? So I told you here. Here.
NAN.
Yeah, it's neighborhood area network. Then, yeah, someone is unmute. So can you mute yourself again? Yeah. So RF mesh is based on radio communication over unlicensed spectrum, such as the frequency of. I just told you. So there are two different types of communication at the smart meters aggregation or meter concentrator section. It's the NAN, which has power line communications, and RF based 900 megahertz frequency. Okay, so what is the energy range of a commercial consumer and customer domain? I recently covered this. So can anyone tell me?
Between 20 to 200 kilowatts.
20 to 200 kilowatt.
Yeah, it's 20 to 200 kilowatt. Next, grid assets are bought and sold in which domain?
Markets.
Yeah. So what are grid assets? It's the energy or support services such as frequency regulation, or I should club them, so like ancillary services. All can be bought and sold in markets domain. So what is or are the boundaries of the customer domain? Can anyone tell me? So a customer has a meter as well as energy service interface, right?
Energy service, both of them. Yes, yes.
Next, ESI is the primary service interface to which domain? Again, it's the same question. Can anyone tell me?
Service provider.
Customer.
Customer, right? So what domain is responsible for smooth operation of the power system?
I think operations.
Operations. Next, the electricity distribution system may be arranged in which of the configurations? So a radial configuration is something like this. You have a point of common coupling. You have loads connected to different buses, each going like this. So this is a radial configuration. Then you have looped. In a loop configuration, what you have is, let's say, here you have generation. Load. You have some more generation. So this is loop configuration, and a meshed is both radial plus loop. So can anyone tell me the distribution system can have is what kind of it has what kind of configuration based on these three options?
Most of the radial type distribution systems.
So it's mostly radial type, but it has loop as well as meshed as well. So it's all of the above. Okay, which of the following regulatory authority regulates tariff, formulates policies regarding subsidies? So CA is Central Electricity Authority, and CERC is, yeah. So
I think fourth option is correct. CTU and STU.
okay, let's expand everything. Then we have Ministry of Power. CERC is Central This is circ, and this is central transmission unit. So now tell me. So I've expanded
Third.
all of the. Yeah,
Third.
it's
Yeah.
the third one. So major amount of electric losses takes place in which side? Can anyone tell me? Is it transmission or distribution?
Major losses occurs in distribution side
Why?
because load is
Hmm. Okay. Who can tell me why primary and secondary distribution have most losses? Anyone? So I mean, you were able to answer, right? Just a second. Yeah. Can anyone tell me?
because
I
I square
think
R loss has more.
Okay, I square R losses are more. That's correct. Why?
I think because with the distribution side, the voltage is less as compared to the transmission side. So that means the current there is more. And then since you are carrying the current, it increases the losses.
Okay. Yeah. So it's not just because of that. It's also
Actually,
because
sir,
distribution.
in distribution, we transmit the power at high, the lower voltage. At lower voltage, current rating is high.
Okay, okay. It's not just because of that. There is one more reason that because it's usually the whole electricity distribution system is usually radial. So there are very long distribution lines connected to different segments. So this leads to various non-technical losses, such as so the loss can have two things. It can be either AT&C aggregated transmission and consumption losses or non-technical losses. What are non-technical losses? Non-technical losses are losses related to, let's say, you are giving faulty readings, or let's say you are bypassing the whole circuitry. Let's say you are putting illegal connections over the distribution system. This increases losses more towards distribution system. These are called non-technical losses. So these are heavy on transmission side. This is not just the only reason. There is one more reason that due to low voltage, for the same amount of power to be transmitted, current is more, which leads to higher I square R losses. One more reason is there due to distribution systems being highly radial, they have longer transmission lines, and longer transmission lines usually have higher resistance, which leads to higher I square R losses. So that's why the primary and secondary distribution systems have higher losses. So now let's discuss some multiple select questions. Just remember that most of these can have, so all of these or most of them can have multiple correct options. So the first one is sensors can be used for the following purposes in the grid. It can detect mechanical failures, tower collapses, extreme mechanical conditions. Second is real-time mechanical and electrical conditions of power lines, diagnose imminent as well as permanent faults. So which one is correct? So second one is correct, right? We can monitor the real-time mechanical and electrical conditions of power lines. So what about A and C?
A
So if there is a mechanical failure, can we detect it? I mean, with the advent of mechanical failure, do current and voltages change, or is there anything that can cause change to them? They can, right? So the sensors can help in detecting the mechanical failures as well. And can we diagnose imminent and as well as permanent faults? We can, right? Reclosers are used in the conditions when there are faults. So, and recloser is a kind of a sensor. So the answer is A, B, and C. So with these questions, you have to carefully assess the options. So think about the options and then come up with why sensors will be or anything will be required or not. So second question, what are the main challenges that the electrical grid faces? Someone has the mic on. Can anyone? Yeah, Dharmendra Kumar Singh, can you mute yourself and just unmute when you have to say something? Yeah. So the second question is, what are the main challenges that the electric grid faces? Anyone? So let's go through. So can we say that increase in energy demand can be a challenge or a threat to electric grid?
Yeah.
Yeah. So increase in energy demand can have can challenge the or have a threat to the electric grid as well. So can the rise of middle class be a potential threat to electric grid? A, B, D. Okay, so can anyone tell me why B is a correct option? So someone just wrote it, Polar. So can you tell me? I don't know if I'm pronouncing it correct, Polish or Polish. Can you tell me if why B is correct? Okay, increase in electricity consumption. Yes. So with rise in middle class, what would happen? So let's say earlier ACs used to be what? It were they were like only people with a lot of money could afford it, right? But now as middle class has started, as the lower class has developed into, has started earning more, has transcended to the middle class portion. So they are also now trying to install ACs. So this is not just that. Mostly ACs have become cheaper as well, right? So more people can access ACs now. So earlier, when there were no ACs, summers used to not feel that hot, I guess. But now, when ACs are there, summers are more hotter than they seem to be 10 years before. Maybe it's due to global warming. Maybe it's due to certain mindset. But due to ACs being purchased more, due to this cooling load being purchased more, the the energy demand is increasing, and hence the rise of middle class can have a potential threat to the electric grid. Very limited customers using electricity. Can it pose a threat to electric grid? No, right? If the customers are not using electricity much, how can it have? Yeah. Global rise in temperature. Correct. Since the temperatures are rising, people uh, uh, are buying more cooling loads or fridge, etc. So the energy demand per capita is also increasing. And reliability and power quality are declining. Is this a threat? How are reliability and power quality declining? Can anyone tell me?
Actually, sir, because of non-linear loads, they cause the harmonics at the point of common coupling. They may affect the quality of power.
Okay. So non-linear loads
Non-linear
were
loads.
there before. Non-linear loads were there before. So why only non-linear load? So first of all, what is a non-linear load? Can you tell me?
Actually, the load
Just give
which
me an
derives electricity,
example. Yeah, just give me an example of a non-linear load.
non-linear load like SMPS, power clearance devices.
Yeah. So
Yes.
why are they being connected to the grid? Due to so they are being interfaced with something, right?
Yes.
So what are they being interfaced with mostly? It's renewables, right? So you have solar PVs, they are being integrated through inverters. Inverters are power electronic loads which are non-linear in nature. So
Yes.
due to the rise in PVs, these renewable resources which are there in solar rooftop as well, or at different uh, places at transmission side also, there is utility scale wind farms and PV farms. So these can deteriorate power quality, thereby decreasing the reliability of our electric grid. So this is also a major threat. So a system that integrates several types of power sources, wind turbines, hydro, photovoltaics, and batteries to give a reliable overall power supply is termed as what? Can you tell me? So when we have multiple different sources of electricity generation, microgrid. So we only have, so do microgrids only have power generations? Don't they have load? So right now we only have several types of power sources: wind turbines, hydro, photovoltaics, and batteries. How can it be a microgrid? It's a virtual power plant. Okay, so what is a virtual power plant? Let's see. So let's say you have a farm where you have storage plus some PVs plus wind turbines. And let's say you are at a place where there is a river where you can generate hydropower as well. So all of these combined, you can be seen as a potential power plant or a virtual power plant. What is a virtual power plant? You are supplying power to the grid. Doesn't matter where it's coming from. I mean, it's not a particular plant like hydro plant or wind turbine or solar storage or PVs. You have a conglomerate of different sources. So these can be seen as a virtual power plant from the transmission side. Hence, these are called, so these are termed as virtual power plant. Next, you have a localized grouping of electricity generation, energy storage, and loads are termed as. Can you tell me the answer for this?
Microgrid.
Yeah, it's microgrid. Great. So next, communication dimensions for smart grid. So the communication for smart grid should ensure what? Should it be reliable? Should it be stable? Should it be understandable? Should it be measurable, available, flexible, clarity? What are the different, you can say, uh, properties associated with a good communication infrastructure for smart grid? Can you tell me? It's a multiple select answer. So it should be reliable, right? If my measurements, let's say, if my communication, if I'm measuring something at some place, but my communication system is not reliable, what would happen with my measurements? I won't be able to transmit them to the dispatch center or the control center. So the communication should infrastructure should be reliable in nature. So it should have reliability. It should be stable as well. It shouldn't be like it transmits at one point and then it doesn't transmit with the second interval or second time interval. Understandability. We don't need it to be understandable, right? It's the measurements that we want. The communication doesn't. It is not the understandability is not a property of communication infrastructure. Measurability, yes. So if we are not able to measure the different communication infrastructures, how would we know which one to establish where? Let's say we have RF, free RF waves at some place. Let's say, so you've heard of cognitive radio, right? What is cognitive radio? It tends to align itself to the radio frequency, which is mostly available at a particular place. So if it's able to measure different, for cognitive radio, it should be able to measure different communication frequencies. Then only it will be able to adapt to a certain frequency so as to transmit the data from a particular site to the different, to a particular place to a different load center. It should be readily available. I mean, if it's not available, what's the fun of it? Then it should be flexible in nature. It should support multiple different, it shouldn't be like it supports n measurements, but for n+1 it doesn't support. I mean, how will I send the n+1 measurement? Clarity. So the communication system must not have noise in it, built-in noise. So let's say I'm transmitting something, but it's coming out to be noisy. So if it's noisy, the measurements will have no use to me. So to make sure that my communication systems have perfect clarity, the communication should have perfect clarity. So next
Hello,
is
sir.
select three. Yeah, go on.
Sir, in fourth question, could you please tell me what is difference between macro grid and micro grid? Once again.
Okay. So both are dependent on the power capacity. So I don't know the exact number, but the microgrid has a lesser power capacity than the macro grid. So macro grid is assumed to have a bigger generating resources connected to it, bigger loads, and is able to supply at islanded mode to a bigger quantity of bigger power capacity. Right now, this macro grid is generally not, this term as such is generally not used, because why would we have something of a large capacity at distribution side? Why not we have it on the transmission side? So that's why we don't generally consider macro grids as such, but these are based on power capacity. I don't remember the exact number, but uh, it's a few megawatt, I guess 10 megawatt or something. So you have to check it on your own, but the threshold is a power capacity. So below it, it's called microgrid. Above it, it's called macrogrid. Does that clear it?
Yes, sir.
Hmm. So we have 6 questions. Select 3 wireless technologies from the list below. So feel free to tell me when you're ready with an answer.
B, C, D.
Yeah. So power line communication is wired. Cellular is not. Cognitive radio is not. Satellite is not. And fiber optic is not. Seventh question. How to manage demand on a smart grid network? Can anyone tell me? How can we manage demand on a smart grid network?
Shifting demand to another time or day. Rescheduling uses.
Uh, I'm not able to hear you. Can you tell it again?
A
Shifting.
option and C option.
Okay, so you're saying shifting demand to another time or day. Yes. Let's say we have EV loads. So if you have multiple different EVs, let's say the distribution system has consumers which have EV connected to them to the residential load. Let's say the EVs are being charged at night when people come back at home, when they have their EVs at home. So what happens in the night? Already you are using cooling loads. Let's say it's a brave summer evening and you are already using cooling loads. So what happens is when you connect your EV to the charging station, it starts charging. So the load increases on the uh, on the on the on the uh, on the distribution side. So when the load increases, the generation at one point when there is uncontrolled charging happening everywhere in India, let's say, the generation won't be able to suffice. So what should we do? We should shift it to another time of the day. We can say, let's say, during solar hours, try and charge your EV. When we have solar hours, what happens? There is an abundance of solar power, and the solar power could be used to supply these EV loads. So, and we can say this, that charge it at the night. Let's say in night to early morning when we don't have peak, when we have valleys. Then use excessive energy. Should we use excessive energy to manage demand at smart grid? I don't think so. So yeah. Tell me.
Sir, in the first option, shifting demand to another time or delay. So, could you please clear something that if my EV require charger at the office time, but the price is high, then how can I shift the demand?
Yes. So yeah. So that's an interesting question. Let's say you have a higher price at, so it won't stay high for for the whole day, right? So it will go down at some point when you can charge. Let's say you are at office. You said you are at office. You go to office at 10 a.m. and let's say you leave at 6 p.m. So the prices won't stay high for the whole time, right? And it can't stay high because you have abundance of solar power available with you. So with solar power, the prices would come down. Right now, don't think of it as a price dependent quantity, because right now we don't use time of use prices at the distribution side. I don't know how you came up with the price concept, but right now assume that it's just a flat retail price that you receive at your home. That's 2 rupees or 5 rupees or 8 rupees per kilowatt hour. So that is what is being expected you from the from charging the EV. Don't consider it as a price based quantity. Look it from the perspective of the operator. Demand is more, because if you charge, the demand will increase furthermore and the system won't be able to suffice. That's why I quoted that example. Okay, so you must not use excessive energy. That's what we told. For from an EV load, if you use excessive energy, then the generation won't suffice. You should consider rescheduling your usage. That's correct. So should we reduce consumption to manage demand on a smart grid network? Yes, right. Obviously, you should reduce consumption. So how can we incentivize consumption to be reduced? Let's say that's what I just said, right? So you are charging at a peak. The EV is being charged at a peak. So you are, if you incentivize the user, let's say, don't charge at this point. I'll give you 100 rupees if you don't charge at 6 p.m. But charge at, let's say, 11 p.m. So the customer receives incentive as well as the load is shifted to a different time. So you want to reduce consumption to be able to manage the grid effectively. Next is power. Pumped hydro power stations are looked as frequency regulators, voltage regulators, bulk power suppliers, or conventional generating stations. So who will answer this?
I think bulk power suppliers.
Okay, so no, these are not bulk power suppliers. A pumped hydropower can't have bulk power. I mean, what do you understand by bulk power? Bulk power is you cater to the needs of the load, let's say 25% or 50%. So that's how bulk power is treated as. So they can't generate this much. So someone said frequency regulator. That's correct. So since you are changing your modulating how, so let's discuss what is frequency regulation. So what is frequency regulation? You are trying to manipulate real power, or I should not say manipulate, I should say modulate. Modulate means to increase or decrease. Modulate real power to ensure decay or rise. That's how you modulate frequency. So how is it? Its generation is greater than load, frequency increases. If it's the opposite, the generation decreases. Now with pumped hydro power stations, what you are doing is when this condition, the generation is more. So you try to act as load and you pump the water from a lower reservoir. We call it lower reservoir. We'll call it LR and HR. So you pump the water to the higher reservoir, and when conditions such as generation decreases to load, so frequency starts dipping. What you do is you send this water back to the lower reservoir through a turbine. Like, I'm not doing a good job, but let's say you are sending it through a turbine. The turbine rotates, is connected to an alternator starts generating electricity. So you're modulating your power consumption, your real power consumption or generation. So your frequency changes. Now someone said voltage regulator. Oh, sorry. Hmm. Hmm. So what is voltage regulator? So one thing I should tell you that real power highly coupled with frequency. So if you change real power, the frequency will change, while the reactive power is highly coupled with magnitude of voltage. So for voltage regulation, you modulate reactive power. Here you are not modulating reactive power. A reactive power is something that is modulated from the alternator. You can have the operation in such a way that the internal EMF of the alternator is at a higher end or a lower end, so as to modulate the reactive power output from the generator. But here you are not doing that, because you are the pumped hydropower is concerned with how you are pumping and then storing the water and then sending it back to the reservoir again to generate electricity and consume load. So the pumped hydropower act as frequency regulator, not as voltage regulator. So can anyone tell me what is a good voltage regulator? Yeah. So don't worry. This lecture is being recorded. It will be posted in the YouTube as well. So very soon you will receive a communication from the I guess NPTEL team, or in your course section on the left hand side you'll have the live sessions, this panel where you can go and click on the links. So I'll send these links to the NPTEL team and they'll convey it to you. So yeah, where was I? So can anyone tell me how can we regulate voltage? What are good voltage regulators?
By changing the excitation.
Yeah. So but what kind of resources are good voltage regulators? We can achieve regulations with voltage regulation with what? So through inverter based resources. So the firing angle at which the power electronic what you say, these power electronic equipments, or the power electronics based uh, resources, these inverter resources, when you change the firing angle, you change the amount of Q that they can inject or retrieve from the grid. So by changing that, you can affect voltage regulation. Here, it's not possible. So the pumped hydro power stations are looked more of as a voltage frequency regulators for the grid. So so this is so I've covered all the aspects. Let me just give you a brief recap of what we did.
Hello,
And
sir.
then, yeah.
Sir, I have doubt in seventh question. Could you please go on that slide, last slide?
Yeah. Tell me.
Yeah. So the last option is in the seventh question, the reducing consumption. Okay. So let's consider industrial load. Okay. So the production company owner wants to maximize the production. So how we will convince that owner to reduce their consumption? Yeah. Could you please explain?
So let's
How
say,
we will
so
incentivize the owner?
okay, that's a good question, but right now I'm just telling ways to manage demand on an electric grid network, smart grid network. But let's take your question for example. Let's say an industrial load, an industry is producing something. So, and it's producing, let's say, material of rupees 25,000 per hour. So it knows it can sell that material for 25,000 rupees, which it generates in an hour, right? So when you say that as a distribution company that take this 100 rupees and decrease your load, will he do that? No, because he knows 100 rupees worth nothing in front of 25,000. So, but what if it's just producing rupees 25 worth of good? It will take that 100 rupees from the distribution company, right? So I won't say that the distribution company or utility must always look for options to decrease the load from the industrial side only. Right now, in this day and age, we as consumers of electricity, we have flat retail price. We pay what, 8 rupees per something for 100 units, then something for 200 units, right? But what happens with industrial loads is that they cross subsidize us. So you must see in these newspapers, right? Distribution companies are in a lot of stress. They have a lot of debt and a lot of over what you say. They have a lot of charges to be paid back to the government, right? But they are not able to do that. Why? Because since it's a flat retail price due to political pressure or something, let's say, they are not able to retrieve back their costs. So what they do is they cross subsidize us to the industrial load. So if you see, industries may have time of usage prices. So with the time, the price of electricity varies for them for a day. So why would they want to reduce consumption over there? They are making money over there, right? So they will never try and incentivize that load because that's how they are getting their money back. They can always incentivize us because we are in a greater quantity. The residential load is still quantifiable enough to be reduced in a way we can manage the demand on smart grid network. So they look for residential or commercial buildings, not the industrial load mostly. But yeah, let's say the incentive offered is much greater than what they have, they will take that offer and the industrial load could be reduced. But right now, in this present scenario, in this day and age, I don't feel a reason to decrease industrial load when that load is powering the distribution companies to reduce their costs. So, is this explanation good enough?
Yes, yes. Thank you, sir.
No worries. So, right now, don't go into prices or what do you say, how price would vary. We are not looking it from a market perspective as of now. We are only looking at from an operator's perspective. An operator would want to reduce consumption to be able to match the generation or load. So always remember, right now we're looking at from the eyes of an operator. But yeah, it's a good perspective to look from the consumer or industrial or customer side as well, because if we are not able to tell how, so let's say I'm using this light, right? I'm teaching you. What if the government decides to reduce load? So I would not be able to teach you, right? And what if they ask, let's say, we'll only give you electricity if you give us 25 rupees per hour? I would have to give them because I need to take this class. So there is a certain maximum willingness to pay attributed to how we consume our electricity. So that is what is exploited in smart grids as well, but we will cover that topic in the later stage. Right now, only look at from the perspective of operator, not from the customer. So is it understood? Does everybody get the gist of it? Yeah, I could really use a yes or a no. So are you comfortable with English? So I have to teach in English. That's what mandated by NPTEL. But if you want to me to repeat something in Hindi, I can always do that. Yeah. So if everyone is comfortable with English, it's fine. Okay. So today we covered week one. So in week one, we started with introduction to smart grids. What are smart grids? Why we need smart grids? Then we went on to discover what are the various architectures associated with smart grids, the different domains. Then we went in depth about various advancements, the smart grid standards, the information system, and other phasor measurement units, and etc. Then we discussed what are distribution automation, and we solved some questions based on that. So that's it for this class. So in the next session, which will happen on next Saturday, 6 to 8, we'll cover week 2, which are electrical systems, I guess, on grid. So if anyone has any questions, the floor is still open. If anyone has questions, I can take one more before I close this session. So is everyone getting right? Can you give me feedback if today's class was good enough, or if you want me to change certain attribute related to that, I can do that happily. Yes, yes. What do you want me to change? Giriraj wrote yes. What do you want me to change?
No, I mean, this is good session. Okay, and
Okay. Okay, no worries. Okay, so see you all next week with week 2. So you can now leave this meeting. No worries. Thank you. So I would have to request you to leave this meeting so that I can close it. Oh, thank you. Ola Shrivali, if you can please leave this meeting. Maitri, Gopi Krishna. Yeah, so please leave this meeting. I can't close it until you all leave, so I have to make sure that you leave it. Yeah, Shrivali, can you please leave it? Yeah. Exit the meeting.